Okay, so this is the outline of chapter 29. So in this chapter, we learn how to evaluate the B field generated by some structure like current, like the moving charge. Or actually, moving charge is like a current. Okay, so actually, the outline here is the B field due to a current, and then the force between two parallel currents, and then the Ampere's law, just like what we learned in the Gauss law in chapter 23. Okay, used for the Gauss law used for calculate the E field, and then the Ampere's law used for calculate the B field. And then we'll learn the solenoid and also the toroid, and the current coil as a magnetic dipole, just a viewpoint. Okay, so this is another overview. Okay, so we actually have seen this table in chapter 23. So at that time, we learned the Gauss law. Although in this textbook, the Gauss law doesn't look like this, but anyway, just an illustration. And in this chapter, we will learn Ampere's law. And actually, in this textbook, the current law, the Ampere's law in this chapter is only up to this part, and this part. For that part, we will learn that part in chapter 32. It is a little bit strange, but it's just like progressively. Okay, so this is like static current, this is like the displacement current. Okay, you'll learn it in chapter 32, so don't need to worry about too much about that. And actually, in the next chapter, we will learn Faraday's law, and chapter 32, we will also learn this one. Okay, the magnetic version of the Gauss law. Okay, so anyway, here first we try to talk about the B field due to a current. How to calculate the B field generated by a current. So here is the so-called the Biot-Savart law. Okay, the law of Biot-Savart, or sometimes we call it Biot-Savart law. Yeah. So actually, what it said is that the magnitude of the field of the B field produced at point P. Okay, so this point is what we concern. Actually, for a structure, for a current, okay, it will generate B field in the whole space, but every time we only can calculate the B field at a point. Okay, after finishing a point, we can of course calculate another point, so on and so forth. So yeah, so even though B field is like the if is a vector field, so it should exist for the whole space, but at a certain moment we only care about a point P like this. Okay, at a distance out by the current length element, ds turns out to be this expression. Okay, so here we have the wire. Okay, we have the wire from here to there, and then the current is like this. Okay, so this wire is not straight. So what we try to do is we try to cut it into small segment. Okay, so up to here is ds, and then of course this ds vector follows the direction of the current. Okay, so the current is like from bottom to top, something like that. Okay, so here for this segment only, ds, okay, is like pointing to the top left. Okay, to the top left. So it is like I times ds. Okay, so I is just a scalar, so we can multiply by the ds. Okay, so this is the IDS. So this part is a small current segment. So it will generate B field in the whole space, and of course at point P. Okay, so here the distance between the current segment to the desired point is r. So we have the r hat. Okay, the unit vector in r direction. Okay, we count it starting from the current segment. Start from the current segment. this is the R axis. Okay, so this is R hat, the unit vector in R direction. Okay, so here it says the dB generated at point P will be like, this is a constant, this is a big constant, okay? And then we have IDS, okay, IDS is about the current. We also have this sine of theta, okay, so you can imagine it should be related to the cross product. And then we also have this R square, okay, we also have this R square. So this is a scalar form, okay, this is a scalar form. Okay, so first we try to consider what is mu naught, okay, mu zero, mu naught. Okay, so, and then also the theta, okay, theta is the angle between the ds and the r hat, okay, from ds to r hat is the angle of theta. So this is sine of theta, and yeah, and then mu zero is another well-known constant in the electromagnetism. So the previous one is the epsilon naught. This is the mu naught. So the mu naught is called the permeability constant. Okay, the epsilon naught is called the permittivity constant. Okay, so so this one in Chinese is called 磁导率. 磁导率. Okay, so mu zero is the magnetic characteristic in vacuum. It's mu zero. If it is in other magnetic material, it could be a mu. Okay, yeah. So so whose value is defined to be exactly mu zero is 4 pi times 10 to negative 7 Tesla meter per ampere, or this value. So usually I actually remember this one, okay, rather than that 1.26 times 10 to negative 6. So this is 4 pi times 10 to the 7th, because it is similar to the actually this one is similar to the Coulomb's force, okay, to the Coulomb's force. If you still remember, the Coulomb's force is like F equals 1 over 4 pi epsilon naught, and then Q1, Q2 over R square. So you can see here, So of course there are something on the left side, and then here we have 4 pi. We have R square. We have 1 over epsilon naught. We have mu naught here, okay? And then finally, Q1, Q2. Here we have something like a cross product. This one is expected to be a cross product. Okay, so this cross product will be like ds cross r hat, okay? R hat, the magnitude of it is 1, so that it won't influence the magnitude, okay? The magnitude or the value in the numerator. Okay, so we have a ds cross r hat here. So finally, if we try to write it in the vector form, the left side will be the dB, the B field, and then this is the constant mu naught over 4 pi, and then we have r square, we have I is a scalar, we also have this cross product. Yeah, because the cross product is like it is like ds cross r hat, okay? ds cross r hat. So you can expect ds is like pointing to the ds cross, okay? ds is like this direction, okay? This direction. And then r hat is pointing to the right side. So you swing your okay. So you cross it to the right side. Your thumb is pointing into the page. So which means that the dB is pointing into the page. This is dB. Okay, so this is called the law of Biot-Savart. Okay, just like other laws. So this is a law, so we cannot prove it. But actually, we can see somehow the duality. Okay, duality here. Okay, so here is like the cross product is like the charge product here. And one other duality is that for many equations for the electrostatics, okay, when you change to the version for the magnetisms, it will be like changing the epsilon naught to 1 over mu naught, or 1 over epsilon naught to mu naught, to 1 over mu naught, something like this. So it's like mu naught is in the denominator, okay, but here mu naught is in the numerator. And these two constants is really important. It's really important. And actually in chapter 33, I think, chapter 33, we will learn this 1 over square root of epsilon mu naught is actually the speed of light. It's actually the speed of light. We can try to solve the wave equation. Actually the wave equation is derived from the Maxwell equation. Maxwell equation is here. So actually in this course we will learn the Maxwell equation until chapter 32. And chapter 33 we will try to derive the wave equation from the Maxwell equation. So we will get the wave equation by solving the wave equation, which is a partial differential equation, a PDE. Then the solution will be the electromagnetic wave. Okay, electromagnetic wave. The philosophy is like this. Okay, so yeah. So actually, by solving the wave equation, we know that the speed of wave, the speed of the electromagnetic wave, will be like this. Okay, related to the mu zero and also the epsilon zero. Okay, so this is the Biot-Savart law. So here, let's take a look how to make use of it. Okay, so the first case is for long straight wire. Okay, so long means infinitely long. Okay, straight wire. Straight is strict. Okay, carrying a current I. So the Biot-Savart law gives for the magnitude of the B field at the perpendicular distance out from the wire, okay, which is this one. We will actually derive it next page, okay, so don't need to worry. So what it means is that suppose we have a wire, we have a long straight wire here, let's say going into the page, okay, from infinitely far away from that side, going into the page until the infinitely far away. Okay, so we have a wire like this. Okay, so it will generate B field like rotating. Okay, rotating around this wire. Okay, so the magnitude. Okay, so you can see the B field line here. Okay, the B field line here. So it's like denser, closer to the wire, and then sparser, farther from it. Okay, so here you can see, suppose we try to fix a current, and then mu naught is a constant, 2 pi is also constant. So this B is only related to the distance. It's only related to the distance. So which means that if R is fixed, which means that it is the circle, okay, with a center at the wire. Okay, so if R is smaller, the B field is stronger. And then the direction, okay, for the direction, we also use the right hand rule. You also use the right hand rule to determine the direction. Right hand rule. Okay, so you use a thumb pointing into the page follow the direction of the current, so your forefinger will be like clockwise. Okay, so you can see all the B field are like clockwise. Okay, so for the bottom case, likewise for the semi-infinite straight wire, so it's either go from this point to infinite far away or infinite far away to here. Okay, so it's the semi infinite. Okay, 就半无穷的。Okay, so for the semi-infinite straight wire, the magnitude of the B field at the okay, so actually it's half of it. Okay, so this is 2 pi mu 0 I over 2 pi r. This is over 4 pi r. Okay, so only half of it. Of course, we will also prove it in between. Okay, so here we try to use the Biot-Savart law to prove the previous two equations. So first, okay, so let's write out the Biot-Savart law to be dB mu 0 over 4 pi, and then I ds sine of theta, and then r over r squared. So this is the Biot-Savart law with a scalar form. Okay, so here we have the wire from here to there. Okay, of course going to the infinitely far away, or going to the negative infinite far away. Yeah, so actually this is the point P. This is the point P we concerned, and actually let's take the axis here. This is 0. This is 0. This is the s-axis. This is the s-axis. Okay, so the top one is the positive s-axis, and the negative axis is pointing downward. So here. So here by calculate, so in order to calculating the total B field, which means that B field, B field should be like integrating the dB from negative infinity to infinity. Okay, so and then actually this is symmetry. So which means that it will be 2 times of integration of dB from 0 to infinity. It will be equal to from negative infinity to 0, negative, because you can always find the part symmetry to it. So this part and this part will generate the same thing. Okay, so the idea here is like we only calculate half of it. So here we try to plug in this expression here. So dB equals this stuff, putting it here. And then mu 0 I 4 pi are a constant. Okay, and this 4 can be cancelled with this 2, down to a 2. Okay, so here we have mu 0 I over 2 pi outside the integration side. And then it remains sine of theta, and then also ds inside, and then also r square here. So at first glance, okay, ds, this is s, this is theta, this is r. Okay, it looks like they are not relevant, but actually not. They are depending on each other. So here, let's take a look at it. So here, this is the ds. Okay, this is the ds. This is the theta. This is the theta. And then actually, this is the r. This is the r. This is s. This is s. We would like to integrate s from 0 to infinity, and then multiply the whole thing by 2. And then let me erase it. Okay, so this is r. Okay, this is the radius. Okay, so finally we can make use of this variable. Okay, but r is not. Okay, because r is a variable. Yeah, r is a variable related to the s. So of course this is a right angle triangle. By Pythagorean theorem, we can we can have r to be square root of s squared plus capital R squared, and then take the square root. So due to the Pythagorean theorem, and then for sine of theta, okay, so this is sine of theta. We would need the sine of theta. So this one will be pi minus sine of theta. So according to high school trigonometry, sine of theta is equal to sine of pi minus theta. Okay, so sine of pi minus theta should be capital R over R. Capital R over sine over small r. So sine of theta equals to this one, and then r is this one. So it makes the sine of theta like this. And similarly, we also change the r squared to be s squared plus r squared. So altogether, including this r squared and also this r, altogether is r cubed. So this is like this cube in the denominator. So altogether we have s squared plus r squared to the 3/2 power. And then sine of theta including this r. And then, yeah, so this is sine of theta, including this r squared, and then ds. Okay, so all the stuff are ready. And then r is a constant. Okay, it's a constant. So we regard it as a constant, and then ds. So only this one is the variable. Yeah, related to the dummy variable. So actually we can do the integration. Actually, the integration will be like this. Okay, s over s squared plus r squared over s squared plus r squared to the square root of s squared plus capital R squared. Yeah, I will not go deep into how we can calculate it, but just an idea is like you try to assume that s to be r tangent theta, r tangent, or maybe tangent phi. Let me see. As tangent phi is r s over r. Yeah, phi should be this angle. S over r. Yes, sir. So should be like this. Okay, so you assume that s to be r tangent phi. So s squared plus r squared will be like 1 plus tangent square will be secant square, and then also ds will be like r secant square phi d phi. Okay, so you do the substitution, and then you can finally get this one. Okay, so you can practice it by yourself for your calculus class. Yeah? So don't try to go through the whole process. Anyway, if you try to evaluate this antiderivative from 0 to infinity, so if you plug in 0, this is 0 over something, okay, 0 over r, okay, which is 0. And then if you try to plug in infinity, it will be like a 1, okay, because this is s, this is infinity squared plus something finite, which is itself, okay, so that this one can be ignored, so that s squared to the square root, which is s itself, so s over s is 1, okay, so this thing turns out to be a 1, So finally, B will be mu naught I over 2 pi r. So this is related to the current itself, and also related to the distance from the current. Okay, so actually this try to prove why this is true, and I would say this one will be used very frequently. We will use it for like more than 10 times later on. Yeah. Okay, so here is the next case is like we have magnitude of the B field at the center of a circular arc. Okay, circular arc. So it's like it's a part of a circle. Okay, so it's a current loop. Okay, for this case it's a long wire. Okay, it's a long wire. So infinitely long wire. So it generates B field to be mu 0 I over 2 pi r. Here, if it is a circular arc, this is I. So the B field generated at the center. Okay, only at the center point. The center point can be expressed with this expression, which is B equals mu 0 I phi over 4 pi r. Okay, so you consider, okay, this expression is not so elegant, but for the special case is like if it is a center of a full circle. Okay, so for the center of a full circle, so which means that here we have phi to be 2 pi. So plugging it phi to be 2 pi here, 2 pi 4 pi cancel to be a 2. So it is a mu 0 I 2 out, okay, without the pi, okay, because you need to be careful. You need to understand, okay, what is it for? Okay, this is for a full current loop. Okay, this is the B field generated at the center. So this is this case. For this one, it is for infinitely long straight wire. So it generates B equals mu 0 I over 2 pi r. So this one for complete current loop. So it generates the B field center to be B equals mu 0 I over 2 r without the pi. Okay, so why this is like that? So it will be, okay, still using the Biot-Savart law, dB equals this expression, and then B equals integration of dB from 0 to phi. So mu 0 I 4 pi, mu 0 I 4 pi, and then also R square are all constant. Okay, are all constant. Yeah, because we are integrating the phi. We are integrating the phi. So in that case, ds is actually R times d phi pi. Okay, with the polar coordinate. Okay, in the polar coordinate, ds is actually the radius times the d angle. Okay, the angle. So so actually, like this one, this integration of ds from 0 to phi will be like integration of r d phi prime from 0 to phi, which is r phi. So this r will be partly cancelled with this r squared down to an r. So finally, we have 4 pi r in the denominator and then mu 0 I phi in the numerator. So this is the expression, or this is the proof of this one. And then by putting phi to be 2 pi, we will have a special case B to be like this one. Yeah. Okay, so here let's take a look at a sample problem so that we can see how we can make use of this formula. So here it says the wire carry current I consists of a current arc, radius r, and central angle pi over 2 radian. Okay, so actually this part. Okay, so this is the central angle of pi over 2, which is the right angle. So the two straight sections whose extension intersect the center C of the arc, what magnitude or the B field, what B field does the current produce at C? Okay, so here we have a segment 1, 2, and 3. Okay, so for the first one, for the first part, okay, so our head is this one, okay, is pointing to the bottom right, follow the direction of the current, and then DS also like no, okay, DS actually follow the direction of the I, and then R is the direction from this segment to the point we concern. This is the R direction, okay, this is the R direction, so R head is the unit vector in that direction, but for this case DS and R head points to the same direction, so actually DS cross R head will be nothing but a zero vector. So for part 1, it won't generate any B field at point C. And then similarly, this part, the part 2 also generates zero B field at point C. So that means that, okay, dB1 is actually mu 0 over 4 pi, and then IDS sine of theta, and then R square. And then for the segment 1, okay, theta is actually 0 degree, okay, theta is, so for this case theta equals 0 degree. So in this case, sine of 0 degree is 0, so this is nothing but 0. So B1 equals 0. Similarly, B2 equals 0. Okay, for that case, theta equals 180 degree, but sine of 180 degree also equals 0. So finally, B3, okay, B is actually equal to B3, which is mu 0 I phi over 4 pi R. Okay, this is what we derived in the previous page. So here is mu 0 I phi is pi over 2 over 4 pi R. Okay, so actually we can just cancel something out. So actually cancel this pi with this pi, cancel these two, okay, not cancel, actually like multiplying together. So it turns out to be 8R in the denominator and then mu 0I in the numerator. And then in this question, it doesn't tell you the value of I and R, so that we making it like this is okay. Okay, so this is a quick, simple question to make you familiar with the Biot-Savart law and also the derived equation. Here is the second one. So here it says two long parallel wires. Two long parallel wires carry current I1, I2 in opposite directions. What are the magnitude and the direction of the net B field at point P? Okay, so here we have I1, we have I2, and then we have point P. Okay, so here I1 is pointing out of the page, I2 is pointing into the page, and then we would like to find the B field at point P. So assume the following values, I1, I2, and then a D. So this is the D, and then this is a y-angle triangle. So you can simply expect that D will be square root of 2 capital R. Yeah, because it is a right angle triangle and then the two sides are equal to each other. Okay, so these are two long parallel wires. So we can use B1 to be mu 0 I 2 pi mu 0 I1 2 pi R, and then B2 to be mu 0 I2 over 2 pi also 2 pi R, something like this. Okay, so here we have r equals d over square root of 2, which is 5.3 over square root of 2, which is 3.75 centimeter. Yeah, here we just scale it by square root of 2, so we make it to be centimeter. Okay, so and then here, okay, here of course we need to determine the direction of the B field. So which means that here, this is the, yeah, actually we actually use the right hand rule, okay? We actually use the right hand rule. For current I1, okay? For the current I1 is pointing out of the page, So your thumb pointing out of the page, and then your finger will be like this. So going to the P there, so it will be like pointing to the top left. Okay, so you can expect B1 is pointing to this direction. Actually, perpendicular to it. Yeah, so for the I2 is pointing into the page. So your thumb pointing into the page, and then your finger will be like clockwise. Okay, so at point P, it will be like pointing to the top right. Okay, top right. Yeah, of course, I2 is stronger. Okay, so B2 is should be stronger than B1. So the precise figure should be like this. Okay, B2, B1. Okay, anyway, the B will be like this, okay? Actually, this one perpendicular to each other. B1, B2 also perpendicular to each other. So the overall B should be like B1 square plus B2 square, and then taking the square root of the whole thing. So finally, it turns out to be mu 0 over 2 pi r, and then we have a square root of I1 square plus I2 square. Yeah, because mu 0, 2 pi r are common factor. Okay, taking the square and then add them together, it will be like the square of this whole common factor, and then adding together, and then it can be factor out, and then okay, going out, it will be itself. So So mu 0 is 4 pi times 10 to the negative 7, okay? So cancelling, so it can be like 4 pi times 10 to negative 7 over 2 pi times r is 3.75, 0.0375 meter. And then square root of 15 square plus 32 square, like this. So this is nothing but 180 mu Tesla. Okay, so this is the magnitude. We also need to determine the direction. So for the direction, we can actually find phi, and then this is 45 degrees. So adding phi to the 45 degree will be the axis from the positive the direction from the positive x-axis. Okay, so phi will be like arctangent of this is B1. Okay, this is B1. So B1 over B2. So B1 over B2. This is whole big thing. This is also whole big thing. But mu 0 2 pi r can be cancelled. So phi turns out to be arctangent of I1 over I2, which is arctangent of 15 over 32. So this is 25.1 degree. So finally, this one we call it theta. So theta will be 45 degree plus 25.1 degree, which is 70.1 degree. Okay, from positive x-axis. from positive x-axis. 70.1. 70.1. So yeah, so this is something like, okay, you have multiple charges, yeah, and then all of them will generate E field. So it asks you what is the total E field in a certain point at a certain point. So here similarly, you have a multiple current at some point, at some place, and then all of them generate B field. So it asks you the B field generate at a certain point, which is like you calculate the B field individually and then vary at them as a vector sum. So the process are similar, just change E field into B field, and then the source will be like the current rather than a charge. Okay.